Hi, I'm Ahmed Sheta. I'm a fourth-year PhD student at Harvard, and I'm excited to share with you the poster that I'll be presenting in this year's Jinx conference. The poster is titled PP Waves and the Hidden Symmetries of Black Holes, and is based on this paper that appeared on the archive earlier this month in collaboration with Dan Capitz. As you all know, there's an emergent conformal symmetry that controls the dynamics of low-energy processes in the background of near-extremal black holes. This conformal symmetry is, of course, the signature of a deep ADS throat that opens up at the horizon near extremality. And in fact, this enhanced geometric structure has been a key step that has led to progress in understanding the quantum mechanics of black holes. Unfortunately, this enhancement only occurs at very low temperatures. And our inability to come up with analogous universalities at arbitrary Hawking temperatures has hindered progress in understanding the quantum mechanics of black holes away from extremality. The theme of this paper is about exploring universal symmetry enhancements in arbitrary temperature Schwarzschild black holes. A hidden symmetry of a black hole system could be seen in the two possible ways of probing the black hole, either by scattering waves and studying the scattering cross-sections and absorption rates, or alternatively by studying the spectrum of quasi-normal modes of the black hole, which is our approach. Quasi-normal modes are discrete resonance modes that are intrinsic to the black hole, which are complex-valued because of the dissipative nature of the horizon. There are two branches of quasi-normal modes that are analytically understood: the iconal spectrum with very high oscillation frequency and the highly damped spectrum with very short lifetimes. Both branches display an evenly spaced overtone structure, which hints at a hidden underlying symmetry that emerges in these kinematic limits. One of the things I discuss in the poster is how this hidden symmetry structure is indeed controlled by universal aspects of black hole backgrounds, namely its bound massless geodesics. In Schwarzschild, there are two classes of such geodesics: the photon ring, shown on the left, which controls the iconal modes, and the horizon generators, shown on the right, which controls the highly damped modes. In fact, there's a universal scaling limit discovered by Penrose that zooms into the geometry seen by any massless geodesics, which results in a PP wave spacetime, which is a more symmetric geometry than the original Schwarzschild spacetime. In a similar spirit to the ADS throat, this enhanced geometry underlies the hidden symmetry that emerges in the iconal and highly damped limits. In particular, the iconal modes are controlled by a hidden inverted harmonic oscillator algebra that emerges at the peak of the radial potential near the photon ring. This hidden structure could be geometrized by scaling into the PP wave of the photon ring, using the Penrose limit. Iconal quasi-normal mode wave functions contract to solutions of the wave equation in the PP wave geometry, and the hidden symmetries become its isometries. A particularly nice fact is that string theory is exactly solvable in these PP wave backgrounds, which was a key in the BMN duality. In the present context, our analysis is a step towards finding a set of well-understood stringy modes propagating on a Schwarzschild background. Another aspect I present in the poster is the two types of WKB approximation and how they're each universally encoded into the wave equation of a PP wave geometry. As a specific example of this, I'll present on the polar motion of non-equatorial photon ring orbits. Of course, in Schwarzschild, these are related to the equatorial ones by SO3 symmetry, but we analyze the problem in the generic non-trivial language that would generalize to Kerr. Finally, I'll present on the analogous story for the highly damped modes. These are controlled by the near-horizon Rindler region, and the equally spaced overtones are generated by the 2D Poincare symmetry of Rindler that emerges in the near-horizon limit. I also discuss how the highly damped quasi-normal mode wave functions are propagated by the generators of the past horizon. Taking the Penrose limit into these geodesics, we get flat space, with the 2D Poincare algebra emerging as its isometry. If you're interested in any of the things that I mentioned or would like to learn more about this work, please stop by my poster, and at any rate, I do look forward to meeting you at the conference, and thank you for listening.